Yo, welcome to the NucleoGenesis project. My name is Dr. James Utley, your resident codebreaker, data scraper. And I'm here to tell you we're at part 10 of this. So, with that, NucleoGenesis is brought to you by Syndicate Laboratories. And I guess I'll take some time here. I am ready to walk you through what's going to happen here. All right, so NucleoGenesis found at syndicate-labs.io. NucleoGenesis is, again, a temporal framework for eukaryotic nuclear blueprint, archival, and reconstruction. Two fractions. Building a nuclear blueprint manifest. That's what we're trying to do. Building a file. Building a file of nuclear, meaning nucleus of a cell, information. Okay, so here we are, part 4. Phase 3, part 4, and this is of the paper, which is part 10 of this whole thing. All right, so here we are, confidence-weighted spatial reconstruction. So this is about an application, so circle back is we have the Nucleo sampler, which is the cryptographic ledger that does the QC and the building to try to build the framework. Then you have the Nucleo builder, which builds the nuclear blueprint manifest with all of the information that you have acquired, both fresh and for long horizon archival, which is the dried blood spot. Now here we are at Nucleo Reconstruction. So Nucleo Reconstruction is an application that is a computational engine responsible for converting the tiered nuclear blueprint manifest, the file that you have made, into an ensemble of physically plausible three-dimensional nuclear reconstructions, right? So it's a nuclear reconstruction model. It gives you a 3D representation, right? And it's all weighted, and it's based on, so the central innovation of nuclear reconstruction is a confidence weighted constraint optimization. So what that means is every structural or regulatory constraint imposed on the reconstruction is explicitly weighted according to the confidence tier. And if you remember, we talked about all the layers, and then we talked about an uncertainty layer, and we talked about a confidence tier in the part 9. So if you haven't seen that, you should go check it out. All right, so we use some formulation, which is the polymer physics formulation. That's to reconstruct a three-dimensional nuclear organization from contact constraints. This genome is modeled in a coarse granular polymer embedded in a Euclidean space, so kind of like a 3D model, right? And the abstraction reflects the physical reality that the chromatin behaves as a long, flexible, self-avoiding polymer subject to both the topology and the nuclear scale constraints. And this is how it's proofed out. But basically, what you have to know is there is an axis, and in the center of that axis is what would be a reconstruction of a cytoplasm. Then as you're grabbing all this information, you're building this 3D model. And that's how you can see the nucleus being built of a single cell, right? So a eukaryotic cell, most likely a leukocyte, right? Either a macrophage or a lymphocyte, or a monocyte or a lymphocyte. And then with that is it's building a 3D model so you, as the user, can physically see how the nucleus is developed and folding and all of that, right? So now it has tiered constraints. So we're going to talk about the energy function with tiered constraints. So reconstruction proceeds by identifying the polymer conformations that minimize a composite energy function. Each term in the energy reflects a distinct physical or biological constraint acting on the chromatin organization, right? And then you have this proof here, which we will look at in a little more deep depth here in this next slide, or the next, I think, right? So this is your E, E stands for energy, right? So we have the total energy of the system. So we have the backbone, we have the excluded volume, we have the confinement, we have the contacts, and we have the compartments. And that is the visual breakdown of E of X. So you can go through this and you can understand what the math behind it is, and some scaling theory, but we know that we know the backbone connectivity, which is here, starting here, right here, is a genomic contiguity that it is enforced through harmonic bonds between adjacent beads. And the equilibrium bond length, or the B0, corresponds to the mean spatial separation expected from chromatin packing density and at resolution. This term prevents physical stretching or compressing of the polymer backbone while allowing thermal fluctuations, right? So basically, it's one way to organize that nucleus in a 3D model. So excluded volume. Chromatin fibers cannot occupy the same physical space. Self-avoidance is therefore enforced via a soft core repulsive potential, right? So the chromatin fibers, right, they can't all, there's a repulsive nature to them, and that's where you get the excluded volume, which means that, like, making sure that there's enough space in between them. because the nucleus is a complex and compact little factory there. Okay, now we have the nuclear confinement. That's the genome is physically confined within the nuclear envelope. This constraint is modeled as a soft spherical boundary, and that's what you're actually going to see in the reconstruction application is that boundary, and then you see the nuclear material, which is very dense. It's like dense blobs in the model, right? So now we have AB compartment segregation. That's large scale chromatin compartmentalization and is captured through an attractive interaction between beads belonging to the same compartment. This term drives segregation from transcriptally from the transcriptome and active and inactive regions, reproducing experimentally observed compartment domains with imposed region positional constraints. Really, what that means is just building it will build the formation, right? So you can see it, in a 3D model. That's what it's really saying. So, right. So optimization strategy, right, is reconstructing three-dimensional nuclear structure from heterogeneous, partially uncertain constraints gives rise to this highly non-convex energy landscape. Multiple local corresponds to distinct yet physically plausible chromatin conformations. And this is a weird little word, and I'm not going to butcher it. Minima. Chromatin conformations, particularly in genomic regions, constrained primarily by inferred or predicted data. As a result, the reconstruction requires optimizing strategies capable of escaping poor local minima while ultimately converging to low energy constraint consistent solutions. So basically, it's just how do you optimize for the model? That's what it's essentially saying, right? So there's a simulated annealing, right? To address this challenge, Nucleo Reconstruction employs simulated annealing as a global optimization phase. Simulated annealing is well suited to the task because it explicitly balances exploration and exploitation at high temperatures. The system explores broad regions of configuration space while gradually cooling, constraints probability mass around the energy for favorable conformations, right? So it's just a kind of a corrective mechanism. That's a fancy way of talking about a corrective mechanism of high heat. Okay, and here's the simulated annealing genome reconstruction. Here's the algorithm, which is right here, which really is just trying to reduce to an energy favorable state. The acceptance criteria allows for energy unfavorable moves, and what it does is it tries to provide a physically reasonable starting point that accelerates convergence without imposing strong bias, right? Like that's what we're trying to do is provide a model that seems reflective enough based on the information you have, but not like overly biased, right? So now here we got gradient-based refinement, right? While simulated annealing excels at global exploration, it converges slowly near the minima. Therefore, once annealing identifies a low energy configuration, we apply deterministic gradient-based refinement to eliminate residual constraint violations. Specifically, when we're using limited memory, which efficiently handles the high dimensional parameter space induced by the polymer discretization. All right. So here we go over this generation and the uncertainty quantification, right? And it gives you a per locus positioned uncertainty. So, we're trying to manage uncertainty and predictions all the way through this project. And this is just one more example of that. And it gives you this 3D chromosome structure reconstruction model. So really the takeaway here on this model, which I think is the coolest thing, is the uncertainty scale. So you're kind of like, you have this computational model that is giving you, your A, B compartments, and it's segregated, and it gives you all the ideas of the structure, right? The functional organization, which is here, right? So you have two compartments, you have the repelling, the necessarily repelling you need, and you need to have a structure, right? So, and that gives you a way to visualize it. Now, the important part is that you have these uncertainty scale. So if you see, these are the uncertain areas, is this blur and this variation, which is a reminder that, there's a computation model, like there's just a lot of computation in here, right? And so there's a uncertainty tier, and that's the correlation between the uncertainty tier. So now we have this proof here that looks at the contact satisfaction score. So reconstruction quality is further assessed using a contact satisfaction metric, which quantifies how well reconstructive distances agree with the expected contact derivative, right? And essentially, this is what it means, the uncertainty scale. Together, annealing-based exploration, gradient refinement, and ensemble sampling, and tier stratified validation establishes nuclear reconstruction as a principled, uncertainty-aware reconstruction framework rather than producing a single definitive structure. The method yields a distribution of nuclear conformations whose variability directly encodes what is known, inferred, and unknown. Closing this loop between the experimental measurement and the modeling assumptions and reconstructed nuclear state is all what it's about. Okay, and here's just more of the tech architecture, right? So written in Rust. It does have a level of Python orchestration because I'm a Python guy. And then the visual layer is TypeScript, even though I don't really like TypeScript. And if you want to see, this is how it's broken down. So we have nuclear sampler, the builder, the reconstruction, and the synthesizer. Those are all of the applications that we have gone over thus far. And the synthesizer being the future, and it's the next thing that we're going to talk about, which is a future-proofed orchestration and archival. But that's it. So it runs the Python gambit. We have this side of the house that is nuclear sampler and the builder, which is written in Rust. Well, they all have some component of Rust, but they have it's like basically Rust, Python, TypeScript, and that's for everything. Okay, and this brings us to phase 4 or part 5, and so that does it. This is part 10 in the NucleoGenesis project, and we're going to stop here for now, and we'll go over the next section tomorrow. But until then, my name is Dr. James Utley, and I will see you in the future. Peace.